Welcome to the fourth instructional video in Unit 3. It says, I can't get this bolt off. Famous quote from Archimedes says, give me a lever long enough and a fulcrum on which to place it, and I shall move the world. So, the learning goals for this particular presentation are that students understand the relationship between force, torque, and distance, and that you'll be able to relate force to kinematics motion, which we covered in Unit 2. You should also be able to give real-world applications of torque, and once again, you should be able to calculate using the formula tau equals Fr. So, what we already know. We already know that force can cause a change in motion for the object, generally shown as acceleration. We also know that the greater a force is applied, the longer the acceleration occurs, so generally speaking, the greater change in velocity. We also know that objects can rotate as well as translate. Remember, translational motion is where the object itself moves like this. Okay, so it's actually moving from right to left or left to right. Rotation is, it's kind of staying where it is in space, but it's spinning around in a circle. Now, what we learned in the lab. We learned that a larger force can actually cause an object to rotate. We also learned that a larger distance from a pivot point can also cause an object to rotate. And we also saw that objects rotate when torques are not in balance. So whenever you have the sum of the torques not equal the sum of the torques, that is where this thing will actually turn and rotate. Now, we said that balance can occur with different forces. Okay, so in this particular example, we have a 3 kilogram mass and we have a 1 kilogram mass. And when we look at it in terms of forces, we would say that there is a force of, I'm going to use gravity as 10 just for explanation's sake. We'd have a force of 10 newtons and a force of 30 newtons. And these are very, very different forces. Both of them are exerted downward and the object doesn't rotate or doesn't pivot. Okay. We also had situations in which you have equal forces that result in an imbalance. Okay, so once again, you see a 10 Newton force here and a 10 Newton force here, and these are the same forces. And when we think about it in traditional force value, these things would cancel each other out. But they don't in this particular case because we have to look at the whole thing, where the force is being applied. We learned that balance only occurs when the force times the distance are equal. So for example, in this case, I have a force of 10 and a distance of, I'm going to call it 1 notch. And here I have a force of 10 and a distance of 1 notch. When I multiply these values out, I get a total of 10 and a total of 10. When these two things equal out, that's when I have balance. That's when I'm said to be in equilibrium. Torque. Torque is what we're talking about when we're talking about whether or not an object will rotate. Torque explains why you have a wrench with a long handle as opposed to a short handle. It basically says the greater the distance, the less force required. Okay, we're going to get into the equation in just a minute, but you have the idea of torque being force and distance. If I were to make the distance here, this R term, larger, I can get the same torque with a smaller force. So if you have a long wrench, okay, you can actually get a much bigger torque applied to it than if you have a smaller wrench. Okay, now also you have the idea of a screwdriver. Sometimes you can hook up a screwdriver, like a hex wrench screwdriver, to it, and you can turn it. But the distance has to be distance that you're causing it to rotate this way. So for example, this right here, if I'm trying to get the wrench to turn, this right here, this distance from the object to where the force is applied is the distance. Okay, if you were to look at it, this is where I'm trying to get the screwdriver to turn. There is no distance because the distance is measured parallel. So this right here will represent a negligible distance and it doesn't actually work that well. Now we have the torque equation. We've already talked about this real briefly. This is the Greek letter tau and it stands for torque. Okay, torque is measured in Newton meters. Okay, a lot of times people get it confused with what's called a joule, but it's not. For right now, it's just going to be called torque, and it's the moment that causes an object to rotate. So every time we're talking about torque, we're talking about an object rotating. We're no longer talking about an object translating. We still have force, and we still have distance. This R term is the distance from the turning point. It's the distance from the pivot point. Okay, it's measured in meters. Now it gets its own variable because it's not just any distance. It has to be distance from the pivot point, and it's got to be perpendicular to the direction of the motion. Okay, next we have an example. It says calculate the torque provided by a 200 Newton force exerted 0.5 meters from the pivot point. You see this picture right here. So we know that we are trying to solve for the torque. We know that torque is equal to force times distance. This right here is our force value. This right here is our distance value. So we can take the two, we can multiply them out, and when we do that, we get a torque of 100 Newton meters. In the next example, it says, Archimedes made the statement, give me a lever long enough and a fulcrum on which to place it, and I shall move the world. Okay, that was in the introductory quote, but it's also in this particular example. In this one, it says, Archimedes is capable of exerting a force of 5,000 newtons, so he can actually take and apply a force of 5,000 newtons. Okay, so we know 5,000 newtons. And then he said he's able to move the Earth. The Earth has a mass of 5.98 times 10 to the 24th. Realize that that's a mass. Okay, since it's a mass, we need to be able to convert it to force. Now, this is where the analogy kind of goes squirrely at this point, because we're going to use gravity of 9 point, or we'll use 10 just to make it easier. Gravity of 10. Now, realize that the gravity on Earth is 10 because of the mass of Earth. But just for illustrative purposes, we want to say, okay, well, what if it's subjected to the same gravitational field as Earth? So we're going to say G is 10 meters per second squared. And then how long must his lever arm be? So I'm looking for this lever arm if the Earth fits on one side of a 12,742,000 meter fulcrum. Okay. In this case, I'm trying to figure out where the torques will be balanced, where the torque equals the torque. So at this point, you would say force distance equals force distance. Now I've already labeled my forces and distances here. So at this point, I would need to calculate the force on Earth. Since I'm multiplying by 10, really all I need to do is take that number and change it to 25. And I'm going to change colors just so it's a little bit easier to see. So this value right here is going to be 5.98 times 10 to the 25th because I multiplied the mass and the gravity together. Now you're going to multiply that by 12,742,000, and that is the left side of the equation. On the right side of the equation, we have the force that Archimedes can exert, which is 5,000 newtons, and we want to solve for the distance of this particular lever arm. So we would multiply the left side of the equation together, 5.98 times 10 to the 25th, and then we would multiply that by 12,742,000. And when we do that, we get an exceptionally large number of 7.62 times 10 to the 32nd. Now on the other side, we have 5,000 R. So we would divide both sides by 5,000. Okay, when you divide both sides by 5,000, you end up getting 1.52 times 10 to the 29th. Okay, what that number represents is that is the distance that this fulcrum would have to be in order for you to be able to see, or in order for you to be able to move the Earth according to this example. Now, just for comparison's sake, the distance from the Earth to the Sun is 1.5 times 10 to the 11th meters. So that means that this distance that this fulcrum would have to be would be 10 to the 18th times larger than the distance between the Earth and the Sun, or a million trillion times larger than the distance for the Earth to the Sun. So it's an exceptionally large distance. The last example says determine the mass of the unknown, determine the mass of the unknown to balance the lever. So I've got an unknown right here, and once again, when we're talking about balance, we're saying that torque has to equal torque. So at this point, we're going to use gravity as 10, and it's actually not going to matter because gravity is going to be in each expression. So you could use 9.8, you'd get the same answer. So at this point, we want to see the force that's exerted. We do mass times gravity. So in this case, I'd have a force of 30 newtons. In this case, I'd have a force of 50 newtons. In this case, I'd have 10 newtons. In this case, 20 newtons. And in this case, it would be 10x. Okay, because I don't know what the mass of that particular object is, but I know I would multiply it by 10 because of gravity. So now I have my forces. Now remember, when you're looking at torque, it's not just force, it's force and distance. So now on the right side of the equation, I would have 50 multiplied by 1 because it's on the first notch. Okay, plus nothing here, 30 times 3, because 30 is on the third notch. On the left side of the equation, we have 10 times 1, first notch. We have 20 times 2, which is the second notch. Now we need to figure out what it's going to be on the third notch. Remember, it's on the third notch. So at this point, you have an algebraic expression in which you have only one unknown. 50 times 1 plus 30 times 3, this is 90, would end up giving you 140 on the right side of the equation. On the left side of the equation, you'd have 30x plus 50. To solve for this expression, you would subtract both sides by 50, and you would get 30x equals 90. Divide both sides by 30, and you would get x equals 3 kilograms. In this next, it says relating dynamics to kinematics. Now, you need to realize, you should have realized by now, that the acceleration that we're talking about in the F equals ma question is the exact same acceleration that we talked about in kinematics motion. So acceleration is the link between dynamics and kinematics. So for example, if I give you a question with an initial velocity, a distance, and a time, and I asked you to solve for the force, you should realize that, okay, well, I need to solve for acceleration, and then the mass and the force equals, the mass and the acceleration equals the force. Okay, so whenever you're trying to go back and forth between these equations, you have to solve for A. That's the link between the two. So you can see some examples of that. This is a 500 kilogram box is being pushed to the right on a horizontal surface with a net force of 100 newtons. So we've got a couple numbers right here. How far will the box move if it was initially moving at 2 meters per second to the right for 10 seconds? So I'm looking for distance. Okay, so since I'm looking for distance, I really want to look at my kinematics motion variables first. I'm given an initial velocity of 2. I'm given a time of 10, and I'm trying to solve for the distance. Unfortunately, all of the kinematics motion equations require a third variable, which I don't have. But I can use my information that I have for Newton's second law, and I can come up with that third variable. I can use F equals 100 newtons. I can use M equals 500 kilograms, and I can solve for A. I would say F equals ma, or 100 equals 500a. Divide both sides by 500, and when you do that, you get 0.2 equals a. So this 0.2 meters per second can now become a given in my kinematics motion equations. So now I would look at if dat, if dat. In this case, I've got the acceleration at 0.2. I've got the initial velocity, that's 2. I've got the time. I'm looking for the displacement, so I would choose the equation that does not have final velocity in it. In our case, that would be delta d equals vit plus 1/2 at squared. Okay, so notice how this comes back. You can't just say, oh, I've done kinematics and it goes away. It's going to keep coming back. So at this point, you would plug in, you would say 2 times 10 plus 1/2 of 0.2 times 10 squared. Well, 2 times 10 is easy, that's 20, plus you have 100, 10 squared is 100, okay, times 1/2 times 0.2 ends up giving us a value of about 10, so you would say 30 meters total. Now if you look, this is exactly what we're talking about in terms of using force to get a variable to plug into kinematics. In the next example, it says a car initially at rest is subjected to the forces below for 150 meters. Determine the final velocity of the car. So once again, I'm looking for the final velocity. So I would say, final velocity equals question mark, and I'm given the displacement, delta d. In addition to that, I'm given the initial velocity because it says rest. So really, if I can get one more variable, I'm on my way. But at this point, I'm just given this free body diagram. Now, if you notice, free body diagram, those two cancel out. So what I can say is that I have a net force, according to the free body diagram, of 60 newtons. Now, I can figure out what the mass of this particular object is by knowing that I have the weight. The weight, remember, is mass times gravity. So when I divide this by, we'll do it by 10. Okay, your teacher may want you to do 9.8, but let's just say 10 for now. Okay, if I divide by a gravity of 10, I end up getting 1,000 kilograms is my mass. Now I've got a mass, I've got a force, I can solve for the acceleration. I'd say force equals mass times acceleration, or 60 equals 1,000 A. I would divide both sides by 1,000, and when I do that, I get an acceleration of 0.06. Okay, it's an extremely small acceleration in this particular example. So now I can do if dat, if dat. I have the acceleration, I have the displacement, I have the initial velocity, I have the final velocity. So I would use the equation that does not have time in it, which is a equals vf squared minus vi squared divided by 2 delta d. Okay, like I said, these don't go away. So at this point you would plug your numbers in. 0.06 equals, I'm looking for vf squared, so that stays the same. The initial velocity was 0 divided by 2 times 150. Now the first thing that you'll notice is that this 0 term is going to cancel out. Anything minus 0 is still 0. In order to solve this, I'm going to multiply both sides by 2 times 150, or 300 if you want to think about it this way. That's going to cancel this term out, and it's going to move it over to the other side. So 2 times 150 is 300, and then 300 times 0.06 gives us a value of 18. So now I have 18 equals vf squared. But that's not the answer. I don't want vf squared. I want vf. So the last step is to take the square root. And when you take the square root of 18, you get the final velocity, and the final velocity is 4.25 meters per second. In this last example, it says a car initially traveling at 25 meters per second on a flat road covers 150 meters in 6 seconds. So I have a car, flat road, 6 seconds. When the engine exerts a force of 400 newtons on the car, determine the coefficient of friction between the tires and the road. So this is interesting because it's like a kinematics motion equation, but at the same time, we're looking for the coefficient of friction, not just the acceleration of the force. So let's look at the kinematics information first. Okay, I have 25 meters per second. It says it's initially traveling at 25 meters per second. So I really would like to find the acceleration. That's really what I want to know, because the acceleration is the link between kinematics and force. So I'd say I have an initial velocity of 25. I have a displacement of 150, and I have a time of 6 seconds. If I were to do if dat, I could say initial, final is not what I'm looking for. I don't really care about that. Displacement, acceleration, time. So I'd pick the equation that does not have final velocity in it, which is delta d equals VIT plus 1/2 AT squared. Okay, at this point you would plug your numbers in. I would say 150 equals 25 times 6 plus 1/2 of A 6 squared. So at this point you would plug in your numbers, and you notice right off the bat that you have 150 equals 150 plus 18A. So you should realize off the bat that this term, in order for this to be true, A has to be 0. Well, if A is 0, that tells me the acceleration is 0. What does that tell me about the forces? That tells me that I'm in equilibrium. So if I were to look at a free body diagram, I would say that the applied force is equal to the frictional force. Since I know the applied force is 400 newtons, that tells me that the frictional force is also 400 newtons. So now I've established the frictional force of the car, and I can say the kinetic friction value is 400 newtons. I'm trying to solve for the coefficient of friction, so in order to do that, I need to know the normal force. Now remember, whenever a car is on a flat level surface, the normal force is the same thing as the weight. So I can take the 1,000 kilogram car, and we've been using 10 for gravity. You can use 9.8 if you're supposed to, but 10 for the acceleration due to gravity. and I get a force of 10,000 newtons. Now I can plug it into the equation Fk equals mu k Fn. Plug it in, and you would end up getting a value of 400 newtons equals 10,000 mu k. Divide both sides by 10,000. Okay, you could see the zeros start to cancel out, and you end up with 4 divided by 100, which is 0.04 is my coefficient of friction. Now there are no units for coefficient of friction because you're taking newtons and dividing by newtons.